So hello everyone. Welcome back to this series, Engineering Mathematics, MTE101. So where we will be preparing to eviscerate, to exsanguinate, to annihilate engineering mathematics. We want to make sure that we get an A, we get first class, a 1, MTE101 classification 1. That is what we want to do. So just follow this lecture series to make sure that you get the most out of it, you pass. Okay, that is all we care about. We care about you and your needs. We care about your degree classification. So please, if you haven't subscribed, please, I think this is enough reason for you to click on that subscribe button right now. So thank you very much. Get ready. Our first lecture is numbers. So let's start. So here is our chapter 1. Our chapter 1 is number systems. So tukutangira pa number systems. That is our chapter 1. Okay. So let's start. Okay, so for number systems, from your A level and ordinary level, I think you have learned that we have different sets of numbers. Number systems. So by now, you must have realized that we have different numbers in mathematics. We have natural numbers, we have integers, we have rational numbers, we have real numbers. Yeah. So we'll start to talk about, let's talk about what is a natural number. Okay. Number systems, number 1, we have natural numbers. Natural numbers. So what is a natural number? These are number system of positive numbers. These are the system of positive counting numbers. So natural numbers are generally counting numbers. When you want to count something, those are the numbers that you use. When you want to count something, you don't start from 0. You just say 1 apple, 2 apple, 3 apple, 4 apple, going on and on. So these are counting numbers. Counting numbers. Those are natural numbers. Okay. So natural numbers are represented, we denote natural numbers by the letter n. This letter n. This is how we denote natural numbers. So n is equal to a set of natural numbers, which starts from 1, 2, 3, 4, 5, going on and on and on. Okay, up to infinity. This is our set of natural numbers. Okay, so another set of numbers is what we call the integers. The integers. So basically the integers, okay, so integers are the positive and negative whole numbers. These include 0. So integers are positive and negative whole numbers. Whole numbers. I don't know if you can see my handwriting here, but we are stressing on the point that they are whole numbers, positive and negative, starting from 0. From 0. Okay, so integers are denoted by the letter Z, or some might want to call it Z. Z. Set of integers. So Z is equal to a set of what? Integers. We said integers, we start from 0, 1, 2, 3. Mind you, we are not just going in this direction, we can also go in that other direction. Okay. So for me, let me just finish this up. So this is a set of integers in the positive. This one, for x is more than what? Or equal to 0. So this is just a set of integers. in the positive side. So integers can also be negative. So a whole set of integers could be like this. This is how I was supposed to represent it in the first place. Okay, z is equal to set of integers. Let's just say and on. Since we know that numbers don't end. Numbers start from 0 going to the left, and they also start from 0 going to the right. So we can start by saying for the left direction, we are going on in the left direction. Then we will say 4, -3, -2, -1. Okay, so 0, 1, 2, and on going there. So this is a set of our integers. Okay, this is a more accurate one. This one is just a limited one. Okay. So with that being said, we will go on to the other type of number that we have. We have what we call rational numbers. Rational numbers, these are quotients and integers. These are quotients and of integers. Sorry, quotients of integers or fractions. These examples may be, we may have 1/3, 4/3, 2/3, etc. Okay. Any of the form P of Q. Any of the form P, Q. Okay. P, Q is an element of our set Z. Okay. It is an element of Z. Okay. So if you look back, we said Z is a set of integers. That is what we've said previously. So this is what we mean when we say P, Q are elements of Z. We just mean that P and Q are integers. That is what we mean. Okay. So we have also to specify that Q cannot be equal to 0, because if Q equal to 0, the fraction will become undefined. We denote the set of all rational numbers by Q. So we denote the set of rational numbers by Q. All fractions or rational numbers, if I may say, P over Q, where P, Q are elements of Z. Okay, or are in the set of integers, where P, Q are included in the set of integers, and Q is not equal to 0. Okay, so this is a set. This statement, this here, is what we have been writing above there. So easy made beautiful. We can represent a paragraph of statements in just a few symbols like this. We are saying that Q, a set of rational numbers, is equal to P over Q, where P and Q are elements or are integers or elements of a set of integers. Okay, and Q cannot be 0. Okay, so this statement right here define a rational number. Okay, so the fourth type of number that we're going to talk about are real numbers. The real numbers. So these numbers are the set of all decimals. Set of all decimals. Set of all decimal numbers. And in reality, most of quantities that we have, they are decimals. Around, but they are decimal. So we denote the set of all real numbers by R. So R, set of real numbers, is equal to Okay, so R is the set of all real numbers. Let me just do this. Or decimals. Okay. Let's say you are given a decimal number of the form example. Okay, I hope you guys can see. Okay, so our example states that a change 3.16792 okay to a rational number, or they might say put it in the form or what we mean is represent the number in form of P over Q. Okay, so we just mean that we want to change this decimal into a rational number. Okay, so we will what you do, the first step that you take when you want to change a decimal into a rational number or into a fraction or into the form P over Q, what you have to do is your first example will be changed 3.16792 to a rational number or to a form P over Q. So this is simple. To change this solution, so this is our solution, 100,000. Okay, so we want to multiply this, the left side by 100,000, then the right side by 100,000. So we will be left with 100x 100,000 x is equal to 316,792. Okay, 1 2 3 4 5 1 2 3 4 5. Okay, so this is what we will have if we multiply both sides, because what we want is just to make this a whole number. Then after that we divide by 100,000 both sides, so that we will be left with 100,000. Okay, divided by 100,000. Okay, so our x will then become 316,792 over 100,000. Okay, so this will be our answer. We have successfully changed what that decimal to a rational number. So for our second example 2, so our second example will be a bit tricky. We will use recurring number. A recurring number or a non-terminating number is a number which goes on and on and on and on and on. It does not terminate. Okay. So solution. Okay, we are going to let let x equal to 4.27519. Okay, so this is our x. So what the trick that works right here is you need to multiply this number by a multiple of 10. That is 10, 100, 1,000, 1 million. Okay, in that order. So you need to find a suitable multiple of x for both sides, left and right, such that when we get that multiple, or when we get the product of those two numbers, we can subtract x, and by subtracting x, the recurring numbers will tally or will be in the same line, such that they will subtract to zero, they will become zeros. Okay, so let me show you by doing, if we do 3 examples, you'll see what I'm trying to say right here. Okay, so we need to multiply this by a certain multiple of 10. Okay, let's, by just looking at this by inspection, I can say that if we multiply this x, okay, this number by 100, we will get 427. All right, if we multiply both sides by 100, x is equal to 427,519. Okay, this is what we'll get. So the natural order of the things here is zvatoda kuita isu toda kuti tikasubtracta x kunoko, and of course in this case tinowana 99x, and tikasubtracta x kunoko vana 19 ava, and as we go on vanofana kualign so that by subtracting this x, this 100x from x, my recurring values they become zeros, anoita mazero. Alright. So just by inspection, I noticed that this is we need to multiply by 100. And you are going to learn this. Don't worry. Not how to feel longer, but don't worry. As we go on, you are going to understand this. Alright. So tika multiply, tika subtract x kuno 4.27519. Okay. Ukatarisa panapa, 3 numbers anangana, but my recurring numbers edu 199 are kunangana futhi. Urikona 19 as we go on, and because our x is recurring decimal on it. So 19 still goes on. Then our 100x is still a recurring 19 still goes on. So if we repeat how many times, if we write the 19s go there and then the 19s going, it doesn't really matter, since we are subtracting the 19s, or the recurring part of these numbers will become zeros. Right? Like my 19 yes I said to subtract anongoita mazero because akangonangana. So for instance, 9 minus 9 is 0, 1 minus 1 0, 9 minus 5 we get 4, 1 minus 7 we have to do this so that we get a 4 right there, and then we cancel this, it becomes 3. 5 minus 3 it's 2. Okay, 7 minus 4 it's what? 3. Okay, so if we subtract here 100x minus x, we get 99x. So 99x is equal to 423.244. Mamma number yes aruko asina basi because tungoti 19 minus 1 minus 1 0, 9 minus 9 0, 1 minus 1 0, 9 minus 9 0. Tichingoenda takadai. Saka they are zeros, they don't matter. So what you want to do is to divide, because it's true that x, and we want to make x a rational number. So we have to divide by 99 both sides. I will divide by 99. So one is x are equal to 423.244 over 99. Okay. So as you already know, Kuti, we want this upper number because according to this, according to our conditions on top here, Trudy P over Q and such that P and Q are elements of what are integers. Okay, so P has to be an integer. This is our P. This is not an integer. This is a decimal. Okay, so what we want to do is to multiply by 100, by 1000. We want to make this 1, 2, 3. Okay, we want to make this, we want to multiply this by 1000 and by 1000, so that we make this part an integer and this part an integer, just like what our conditions are telling us to do. So x will then become 423.244 over 99123. This is our answer. No say yakadai, so it's still correct. Yakadai. Ipanja pa calculator, if you notice, if you put it on the calculator and then hit this, you get the exact same value that is right here for x, 4.275, and then the 19 is recurring like this. So this shows that you've nailed it. Watutora masag mama answer yes. Watora answer, watora mama marks yes, I mean you've sucked all the marks into your bag. So this is our example 1. Okay. So I'm just going to do 2 examples with you and then leave you an exercise for you to practice. Okay. So I've shown you the way to prove that your answer is correct. So always, because in mathematics, these are this first section about numbers is the easiest part. So you need to make sure that you collect all the marks, because that is all we care about. We want all the marks. Remember what these 2 dots are telling you is these 2 numbers are repeating themselves going in this direction. Okay, that is what it means. So we want to convert this in the form P over Q, where P, Q are elements in Z and Q is not equal to 0. Okay, that is what we want to do. So what you want to do is we want to let x equal 2.14343. You put your dots on top like that. Okay, so after that, what you want to do is we want to arrange, we want to find a multiple of, we want to multiply the x by a multiple of what? By a factor of 10, or by a multiple of 10. Okay, kuti tuda multiply na, it's either 10, 100, 1000 or 10,000 or 1 million, such that tikam zona minus x isusu tikazo multiply minus this answer isusu pa number ya theta 1 iyoyo, and ma recurring numbers edwa aninga akanangana. subtraction yedu anofana kunangana so that anoita mazero ese. Ndo zvatirongona, tirongoda kuti aite chi, aite mazero handiti. So toita sei, want to make sure that the 4 threes tally, or they are right on top of each other, so that when we subtract they are zero, they become zeros. All right. So if you look at this number, okay, let's see, if we multiply it by 100, let's see, we just see. All right, okay. So let's do trial and error so that you learn the thought process. All right, let's do trial and error. Let's say that we have multiplied it by 100. Let's start by 10. Okay, so if we multiply it by 10 and trial and error, trial and error, right? That is what we're going to do. So ngati we multiply this number by 10 and so that 10x is equal to what? 21.4343 and ati wamarigerenga zvichienda zvakadai. Tikazominus x wedu tikuziva kuti isusu ndi 2.143 and 43. So if you look right there and 4 uyu na 1 uyu vakanangana, 3 uyu na 4 uyu vakanangana, 4 uyu na 3 uyu vakanangana, 3 uyu na this one vakanangana. So we cannot multiply by 10. This is not what we want, because our numbers will not tally. Okay. If we write this clearly, this that I've written here, it's 21.4343 like this. Then it's 2.14343. This is 4. Okay. So ukatotarisa up. If you look closely, these numbers cannot, these recurring numbers cannot subtract each other to give zeros, because they are not right on top of each other. So 10 cannot work. So 10, disregard 10. 10 does not work. So let's go to 100. Let's say 100x is equal to, if we multiply this right hand side by 100, it will become 2.14343. We multiply it by 100. It's 1, 2. Okay. So the comma is right there. Okay, 43 right there. So if we subtract x, our x is what? It's 2.14343, and then it recaps. So if you look at this, the recurring numbers now, they are right on top of each other. We can, if we subtract them, they can be zeros. It does not matter how many numbers we write, 43434343 in this case, and then 4343, they will still subtract to give us 0. So that is what we want. So this is, so for your trial and error, you can find another piece of paper just to try, okay, your numbers, to see which multiple is the best. But usually you don't make 2 trials. Just after 1 trial, the second one will be correct. Okay, so because it's all about the number of zeros, okay, the number of zeros that you are adding there. Say that if they are even, or some you need to multiply by an even, then the other one you need to multiply by an okay, so let's leave that part. So we are saying if we subtract right there, these numbers will become zeros. These recurring digits will become zeros. This will become 2. This will become 2. Okay, this will become 1. This will become 2. Okay, so this is what will come out as a result, and this one will be 99x. Okay, so after this, we want x. So our x will equal to, we divide by 99 on both sides. Will equal to 212, 2 divided by 99. Okay, but always remember, we want this x to be written in form of p over q, a rational number. So p has to be an integer, q has to be an integer. But in this term, in this case, p is not an integer, it's a decimal. So what you need to do is to multiply this, so that this by a factor of 100 on the denominator and also the numerator, so that on the denominator and also the numerator, so that this part becomes a whole number, or it becomes an integer. Okay, so if we multiply this by 10, okay, over 10, we will get to a point where 2122 over 990 will be our what? Will become our answer. Okay, so if you want to test if this is correct, you can just come on the calculator and then say, so this is your answer. You can just come on the calculator and then say 2122 over 990. Okay, so if you it can be reduced to 1051. You can also reduce it to 1061 over 4955. Okay, so you can also decide to write it like this. Either way, the answer is correct. So if you check this one, this is the same number that we've started with, which is 2.14343434343. Okay, so this is Now correct. So let me give you one last example. Let me check examples. Okay, so let me do one last example and then give you one last and then I will have to give you one question to exercise on. Then I'll give you, then always check that package that I send you on Telegram. That package, yes, you can find other examples to practice on. Then so example 3. So these examples are from the past papers at the University of Zimbabwe, and also the notes at the University of Zimbabwe. This is where I'm getting the examples, past papers, tutorials, notes, etc. So when you read, as you read your notes, you will meet exactly these examples. Okay, so the other example is 0.213. All right, so 0.213. Let's see which part is recurring, which part is recurring. Okay, so all these are recurring. So what it means is, what this means is simple. We are saying that all that other part is recurring. We are saying that after 3 we have 213. After every 3 we have 213. So all the 3 digits are what? Are recurring. Okay. So our example 3 in English, 0.213. All right, so 213 and recur. So it's repeating itself. So it's 0.213, 213, 213, 213, 213, and it goes on like that. So our solution, remember, but we are supposed to write the question. The question is 0.213. We have to convert this one to a rational number, or to a form P over Q, where P and Q are elements of Z, and Q is not equal to 0. So the solution will be, first we need to do trial and error. We need to let x equal to 0.213, our recurring. Okay, so we need to do trial and error to make sure that, so that because zvinofana kuti ndezvekuti tiri multiply the left hand side by a multiple of 10. It's either 10 or 100 or 1000 or 10,000 or 1 million. So I did that left hand side, knows that right hand side, which means right hand side to multiply. And there is the question is to multiply side question. The reason is, we want to subtract the answer that we get when we multiply, and we want to subtract x from the answer that we get when we multiply, such that but no subtract, and these recurring digits are aligned so that they become zeros. We want to make these recurring digits zero. Okay, so try 1. So that I'm going to go example 2. So let's try. So try 1. So let's start by maybe. So let's start by multiply by 100, or let's start by multiplying by 10. So 10x will equal to 2.13213, like this. This will be our 10x. Okay, so if we write x directly below 10x, it will be 0.21321, then 3 is right there. Okay, so if you look closely right there, our recurring digits are not directly aligned. 1 minus 2, it does not give us 0. This does not give us 0. These recurring digits 213 akanangana 321. So this does not give us zeros. So 10 hide. So we disregard 10. So trial 2. Okay, we multiply by 100. So always remember, you will never get to more than 3 trials. Usually it's 2. You have found the right multiple of x. Okay. So if we multiply by 100, we have 100x. It does not work. Okay, so let's go to trial number 3. Trial 3, 1000. So 1000x is equal to 213, 213, and then these are recurring. Then if we write x, our x, sorry about that. If we write our x, okay, directly below the 100, below 1000x, we have 0.213, like this. You will see that our recurring digits, they are now directly aligned. 2 anangana 2, 1 and 1, 3 and 3. So we'll just subtract. Okay, so it's like we are subtracting x from the left hand side and then subtracting the value of x from the right hand side. Okay, so from the left hand side we'll be left with is it 99999x. is equal to, let me check, 1000 minus 1 minus 1. I don't want to be, 999 is equal to, then if we subtract there, we get 213 only. Okay, so our x will become 213 divided by 123. Okay, so this will be our answer. Okay, I hope you can see this will be our answer. So to check if our answer is correct, we can just punch it on the calculator, 213 divided by 999, sorry, to get 0. So this is exactly what we started with right there. So if you want to write this as a reduced to its lowest term, when you punch it on the calculator like this using divided, this divide not over, it will first give you this. So this form is a reduced form of this. It's reduced to its lowest term. So this is also 1 over 333. Okay. So those are the examples. So right after this, I hope I remember to just put a question for you to practice. Just one question. Okay. Others, you have to go to the books that I referred you to and then practice those questions. Okay, thank you.